Hello everybody, thank you very much for joining our talk on 4-dimensional X-ray tomography at UGCT-Woodlab. First of all, who we are and what do we do? So UGCT is a consortium between 3 laboratories at Ghent University: radiation physics, full-scale processes in geomaterials, and wood technology. We also have a spin-off company, XRE, that builds our systems. When we joined, we developed a system dedicated to wood science, nanowood. It is very unique. It has 2 X-ray sources, 2 detectors, and can reach resolutions down to 400 nanometers. With it, we were able to build some experience, and also in the meanwhile, XRE is now part of TESCAM. Recently, we are studying dynamic processes more and more. Today, we wanted to show you a couple of our experiments that could perhaps translate into your research. The first is a compression experiment. We have access to a compression stage that is compatible with CT. That is, we can look at a sample in 3 dimensions at the micrometer level while it is being scanned. The resolution is somewhat limited by the size of the device, so we can only reach about 12 micrometers at Hector, which is a scanner of Ghent University, which you see on the right. For this experiment, we chose a step-and-shoot approach that is compress up to a certain level, hold the tension, and scan the sample while it is stable, and then resume compression. The goal of that experiment was to answer how the microstructure of load-bearing panels, such as OSB, behave under load. Naturally, if you apply a higher compression, the structure shrinks. So here you see a couple of vertical slices through the 3D volume. However, because it is high resolution and fully 3-dimensional, we can zoom in on any feature we'd like. For instance, here we show a wood flake that is surrounded by relatively large air cavities. And what's particularly interesting about it is that at the last compression on the right, you see that the wood structure compressed, but there still remains relatively large air cavities. That was kind of a surprise to us. We also did more quantitative analysis with image processing. We segmented the air and the wood phases and looked at the evolution of the air phase through compression. More details can be now found in this paper, which was published about a month ago. The second experiment that we can show you is about hygroscopic swelling. Again, we rely on a device to generate a flux of moist air. This moist air, however, needs to be contained in a CT-compatible climate chamber. This we designed ourselves back in 2014. Mounted on one of the tubes at nanowood, we could reach a resolution of 2.5 micrometers. And with this setup, we were wondering how does the deformation of MDF under water absorption start? What makes it so that it swells so much? So we acquired scans now in a dynamic way, so we did not stop in a stable state to acquire a scan, which means that we reconstructed blurry images. However, this does not mean that we cannot use this data, because as we have a time series, we can effectively compensate these motions and retrieve a time series of sharp images with a framework that is presented by Describer in 2018. From a series of sharp images, we can apply digital form correlation and look at the vertical strain field. And more specifically, we can look at the singularities in the vertical strain field. We can overlay this field with the microstructure of MDF to look if there is any feature that sticks out. Or alternatively, we can derive information about the microstructure first and then overlay it with the strain field. Here, the information that I show in the background, in the grayscale image, is local average of the wood fiber wall thickness. This is still work in progress. Anyway, thank you very much for your attention. If you have any questions, I'm still here. Thank you.